So this is what's called our longshore transport problems. So for this one, we're given a beach where we have waves that are breaking at a height of 0.5 feet and a wave breaking angle of 20 degrees. And then it asks us to calculate the longshore transport in cubic yards per year. And now just a notation that you might see elsewhere in this class, like cubic yards per year can either be written as YD to the third yards cubed or just CY, CY for cubic yards, right? So these longshore transport problems, there are 5 base equations, and the way this is going to work is you're going to start off with the first one, and then you're going to work all the way through to the end, and then the end will spit out the answer in the correct units. So the key to this is you have to enter the problem with your wave breaking angle in degrees, and then either the problem will give you the height of the waves that they break in feet, or the depth of water at which the waves break in feet, right? So you have to be given either one of those, and you'll see why when we do our first equation for these. So the first base equation you've got for these problems is that the wave breaking height is equal to 0.9 times the depth at which the waves are breaking. All right. So this is where it can come in that either one of those two things can be given by the problem, because then you can just immediately calculate the other. So for us, we have 0.5 feet for the wave breaking height is equal to 0.9 times the depth at which the waves are breaking. So the waves are breaking at a depth of 0.556 feet. All right. So next up, we want to calculate the group celerity of the waves while they're breaking. So that's going to be the square root of acceleration due to gravity times the depth at which the waves are breaking. So easy enough. 32.2 feet per second squared times our newly calculated 0.556 feet, and then square root, and we get the group celerity of the waves as they're breaking as 4.23 feet per second. All right, so next up is kind of our wave energy term, right? So that's going to be E sub B is equal to density times gravity times wave breaking height squared over 8. And now that density is always going to be, for these problems, 2 pounds times seconds squared per foot to the 4th. Now, you're probably looking at that thinking, well, those are really weird units, right? Well, it's just an odd combination of, it's just a rearranging of all the normal values you would kind of see for density in this. So it's weird, but again, just got to roll with it, right? So we're going to plug everything in. We're going to have 2 pounds seconds squared foot to the 4th times g, 32.2 feet per second squared, times the wave breaking height, 0.5 feet squared, all over 8. And remember, this is because, right, density is normally mass per unit volume, right? However, in the English system, pounds is a unit of force, not a unit of mass. So those others, that second squared and that extra foot term, are all from the fact that we've included pounds, which is a unit of force, in what's normally a mass divided by a volume, right? So again, don't get too worked up or wrapped up in where that came from. So we go ahead and plug everything in. We get our energy out 2.0125 pounds per feet. And you're probably starting to notice that the units are really weird for these problems, right? Well, what you're going to see from the last equation is that it's based on an empirical correlation. It's based on measured data, right? So the whole point of this is if you go in feet for your height or depth and angle for your or degrees for your angle, it will spit out the correct units in the end, again, because it's an empirical correlation. So now that we have those, we move into the first of our transports equations. P is equal to our energy term times our celerity times the sine of the wave breaking angle times the cosine of the wave breaking angle. We go ahead and plug in 2.0125 pounds per foot times 4.23 feet per second times the sine of 20 degrees times the cosine of 20 degrees. We get 2.74 foot-pounds per second feet. Again, odd units, keeps happening. However, we're getting to our last equation where the actual longshore transport is 7,500 times our p-value. So the way this works is that 7,500 has built into it all of the conversions necessary to go from those weird foot-pound per second foot units to get all the way to cubic yards per year, right? That's all built into that 7,500 number. So we can just plug this in foot-pounds, second feet, and we get that our longshore transport is 20,518 cubic yards per year, can also be written as CY per year, right? So what do you need to take away from these problems? They're going to go the same way every time. You got to use all 5 of those base equations. They're all on the equation sheet. And you need to make sure that you start off in feet for your wave height or your water depth, whichever one you're given, and degrees for your angle, and the units work. All right, and then you get your answer in cubic yards per year.